time, which was in the pool boiling curve. And here, again, the pool boiling curve is an expression of the heat flux as a function of the excess temperature, which is defined as a saturation temperature subtracted from the surface temperature. So that here on the x-axis, we have the excess temperature, which is just some number of degrees above the saturation temperature for the fluid that is changing phase or that's being boiled. Here, this is the pool boiling curve for water at 1 atmosphere. And we consider that there are 4 regimes defined for pool boiling: natural convection, nucleate, transition, and film boiling. The expressions that we have for the heat flux that describes the heat flux as a function of excess temperature, all of those look different because the physical mechanisms responsible for heat transfer during each of these regimes is different. So you'll see different properties associated with each of the fluids, or different properties of the fluids in each of those expressions of correlations that define heat fluxes. Now, unlike in chapters 7 and 8, where we had expressions of Nusselt numbers, dimensionless parameters, for which we could write different types, write expressions for, whether was it laminar or turbulent, was it developing or fully developed. In boiling heat transfer, the expressions of the heat flux are specifically given because different fluids have different temperatures at which, let's say, nucleate boiling might start to occur, or that the film boiling regime might actually exist. And the fluid properties have so much to do with the consideration of when does boiling start, such that vapor bubbles are formed on that solid surface where the liquid is changing phase. When we consider this film boiling, we're considering that there's a vapor blanket that actually separates the liquid fluid from the solid surface where heat is being added. So instead of seeing Nusselt number correlations for boiling, you'll see actual expressions for heat fluxes based on the regime or the point in a regime where that expression of a heat flux is actually defined. Now, from this curve, this green curve here, all right, this is that pool boiling curve. And from this curve, if we read off the y-axis, the heat flux, and the x-axis, the temperature difference, the heat flux for boiling is the heat transfer coefficient times the excess temperature. So if we rearrange this expression, we get that the heat transfer coefficient that will be associated with the boiling is just the heat flux that is heat flux by boiling that occurs divided by the temperature difference between the surface and the saturation temperature. So we can get expressions for heat transfer coefficients all along this curve when we're using water at 1 atmosphere for the boiling. Now, again, this expression that we were looking at the very end of class, this is just an expression. These arrows indicate what happens when we increase the heat flux into a quiescent volume of water, so that we go through the regimes of natural convection to nucleate boiling, transition boiling, and film boiling. The transition boiling is along this dashed green line, and this is actually not a portion of the pool boiling curve that you can get at what is called a heat flux controlled experiment. These orange arrows indicate the direction for heat transfer as we heat the fluid, as we move up or heat the surface, so that heat transfer occurs into the liquid to get to the boiling regimes. If we increase the heat flux, meaning we move along this y-axis, the excess temperature will increase as we increase the heat flux. When we get up here to Q dot max, which is the critical heat flux, this is the point at which we're generating the maximum number of bubbles that we can during what's called the nucleate pool boiling regime. But then we have this sudden jump in temperature from point C to point E. And that's because at this point is where this film blanket or this vapor blanket would occur because the nucleation of bubbles on this surface is continuing to occur all the way until we get to point C, and then those bubbles coalesce into a film. So if we're applying the heat flux is still there, but because the physical phenomena responsible for removing heat from this surface now changes. Instead of liquid becoming vapor in the nuclear pool boiling regime, we actually have to transfer the heat through this film blanket, which would be by conduction and radiation. And it requires a much higher temperature to support the same heat flux. And then we move along the rest of this green line in the upward direction. As long as this surface doesn't melt when it gets to these higher temperatures, you can continue putting heat in, and the temperature, the excess temperature, will continue to increase. Now recall that this is on a log plot here. When we get out here to this red point along this green line, if we start to reduce the heat flux, just turning the power down to the resistive heater that might be provided, or if it's a flame front, whatever is being used to provide a heat flux here, if we reduce that heat flux, when we get down here to point E, it doesn't just go back over here, because this is the point at which the film blanket formed at this heat flux that's over 1 million watts per meter squared. As we reduce it to less than 1 million watts, well, what happens is that the amount of heat that's required to maintain that film blanket is still satisfied as we move below 1 million watts here, or 1 million watts per square meter as a heat flux, until we get all the way down to the Leidenfrost point. And at the Leidenfrost point, that's a condition at which the heat flux associated with that point is not high enough to maintain the vapor blanket. So then the vapor blanket dissipates, and this liquid water that's above the vapor blanket can now hit the surface. It dramatically cools off the surface from this temperature at point D down to a temperature that is in the realm of what is called the nucleate boiling. And then the temperature continues to decrease if we continue decreasing the heat flux. So along this orange line is actually the only portion, these are the only portions of the pool boiling curve that you can reach by doing what's called a heat flux controlled experiment. So from here up to here, this is what we can get in the heat flux controlled experiment, which includes the natural convection and the nucleate boiling. Here along in the film boiling, and all along here in the film boiling, we can get all of those portions of the curve. But here in this dashed line, this is a temperature controlled experiment, which is not the kind of condition that is used for heat transfer that is supported by boiling. It requires a relatively complex experimental setup to actually control the temperature rather than a heat flux. And it actually requires that you have instead of a surface where we're supplying a heat flux, you might have a tube that has superheated steam in it, where you are changing the pressure of that superheated steam so that you actually can control the outside surface temperature rather than controlling the heat flux. You still get a heat flux, but rather than the heat flux being controlled, you actually control the surface temperature, meaning that the x-axis is the independent variable rather than the y-axis being the independent variable that you actually control. But we don't really have to consider that, but just know that between C and D here, this is not a part of the pool boiling curve that you would control or get to by controlling the heat flux that we put into the liquid water to get a boiling to occur. Now, all of these expressions, well, here just written again, this schematic here, or this figure, just is an indication of all of the correlations. Actually, I won't say correlate. Well, yeah, correlations that have been developed. They are empirical correlations that describe heat transfer during natural convection, nucleate boiling, and film boiling, with specific equations or correlations that tell us what the values are of the critical heat flux and this minimum heat flux, which is that Frost point. All of these expressions, just bring them over here, I took from your text here. When we consider nucleate pool boiling, which is where we typically are going to operate, here the critical heat flux at Q dot max, which is up here. This is that maximum heat flux that can be attained during the nucleate pool boiling just before we would transition over to film boiling. This minimum heat flux is associated with the Leidenfrost point. That is the one that's here after coming down from film boiling. What is that minimum heat flux that we would have to get to if we got to a film boiling condition and we wanted to eventually get back to nucleate pool boiling? This is where we'd have to get this heat flux down to. And then once we're in the film boiling range, this is how we would calculate the heat flux. Now, there's no correlation here for the natural convection relations because the natural convections are actually for the boiling heat transfer would just be water in as the working fluid for correlations developed and presented in chapter number 9. And again, technically, it's not actually boiling because during natural convection, there are no vapor bubbles being produced in the natural convection condition. So for nucleate boiling, film boiling, the critical heat flux, and the minimum heat flux, we have these correlations here that define the heat fluxes. And again, for each one of these heat fluxes, according to the regime nucleate or film, or these points where the maximum heat flux is just the maximum heat flux for the nucleate pool boiling, and the minimum heat flux is the minimum associated with film boiling. But for all of these can be related to the expression of a heat flux by boiling. That is just the heat transfer coefficient times the excess temperature, the surface temperature minus the saturation temperature. Now, notice that for each of these, there are different properties, different variables that are a part of this expression. During nucleate boiling, we have vapor bubbles, and we also have, of course, the liquid water that is moving. The properties that are quite important here, these are the dynamic viscosity. This is supposed to be an L. It looks like a 1, but it's an L. It's the dynamic viscosity of the liquid, the latent heat of vaporization associated with the saturation temperature, of course, because we are changing phase, producing bubbles. We have the density of the liquid phase and the density of the vapor phase, row 1 and 2. The specific heat of the liquid phase, the Prandtl number of the liquid phase, gravity, the surface tension of the fluid. And then we have this expression, this constant here, C sub SF, and it's just a constant associated with the particular surface on which boiling is actually occurred. It's an experimental constant that depends on the surface liquid combination. And there's a value N on the Prandtl number. It's another experimental constant that depends on the fluid. So when we're considering calculation of a heat flux in the nucleate pool boiling range, this is the expression that we would use. Now, why do we have all of these properties here? Well, we have vapor bubbles and we have liquid water. So in the correlations that are developed, this density difference between the two fluids is used to calculate or consider the buoyancy forces that will be acting on a bubble that is formed on the surface. So if I imagine a surface where a bubble forms on that surface, well, we would have buoyancy forces acting all around that vapor bubble that seek to push it up and away from the surface. But we also have the surface tension that is occurring, that's between the liquid and the solid surface that this bubble is forming on. So we have to balance the forces until the buoyancy force is greater than the surface tension forces, the bubble will stay attached to the surface. But once it grows large enough, displacing enough of the liquid around it, the buoyancy forces become higher than the surface tension forces, and the bubble can move away from the surface. So in this expression for the nucleate pool boiling, we find a surface tension because the surface tension forces are going to have an effect on the heat flux, because the rate at which bubbles can be formed on the surface is going to give us an indication of the rate at which heat can be moved from the surface. Because the more bubbles that I can get to form and detach and move away from the surface so that liquid comes back into contact with a nucleation site, the higher that heat flux will be. But again, we have to consider that the buoyancy forces would have to overcome the surface tension forces that would hold it on the surface. Now we find the specific heat of the liquid phase, the dynamic viscosity, the Prandtl number. All of those are important because you have to imagine that there are multiple bubbles forming and moving off of this surface, so that the fluid is actually moving, and the heat transfer from this surface, whether there are bubbles forming all over the surface or only at particular points along the surface, there would be fluid moving over this surface, so that there would be a heat transfer coefficient associated with not only the change in phase of the liquid to a vapor to produce these bubbles, but also all of this fluid would be moving over the surface. So this expression for a heat flux in the nucleate pool boiling range is one that takes into account not only the latent heat of vaporization that is removed from this surface, but also just the general movement of the fluid. Now, to find this constant C sub SF and this constant N, we have to go to some tables here. And let's see, where is it? Here we go, table 10.3. So depending on the fluid surface combination, we have these expressions of these constants that are, again, experimentally determined so that they will be substituted into that expression. Now, these other two tables, 10-2 and 10-1, are expressions of the surface temperature or surface tension for water when we have what we consider a temperature dependence of this expression of the surface tension that would be in the denominator of this first ratio that we find in the nucleate pool boiling heat flux, or nucleate pool boiling heat flux determination for when we're using water. If we're using other fluids, we have these expressions of the surface tension as a function of temperature for all of these other fluids that we might be considering boiling, for which we might be considering boiling to occur. But for any of these other fluids, we would also need to get the properties. Let's say if we were boiling ammonia, then we need all of the properties associated with the ammonia, including its latent heat of vaporization, its specific heat of the liquid phase, along with its surface tension, the density difference between the liquid and the vapor phases. We need all of those things in order to actually calculate that heat flux. But that's where we would get the quantities for the determination of the nucleate pool boiling. Now, all of these properties would also be evaluated at the saturation condition. So the dense or the specific, or the dynamic viscosity, the latent heat of vaporization, the densities. So this would be the density of the liquid and the density of the vapor phases at whatever the saturation temperature is, the Prandtl number. All of those properties would be evaluated at the saturation temperature for those, for that whatever fluid is actually being boiled. Now here, for that maximum heat flux, this is at the end point of the nucleate pool boiling range. So here, just going back, all of this is this section here is nucleate pool boiling. At the very top of this nuclear pool boiling range is the critical heat flux. So if we want to determine, well, what is the critical heat flux for a particular fluid, then here we just would use another expression for the determination of that heat flux, where it's going to include the density of the liquid and the vapor phases, gravity, the surface tension of the fluid, the latent heat of vaporization, and this C sub CR, another it's another expression of an experimentally determined quantity. And I'll see that there's another table here, 10.4, where we have values of C sub CR. But here, this expression, notice that this particular expression does not include C sub SF or N, so that in C sub SF, 10 dash is where we get the magnitudes from 10-3 for the use of the nucleate pool boiling heat flux. Here, this is the critical heat flux. So here, this constant is just based on another set of parameters that were experimentally determined to be most significant when calculating that heat flux. So here, depending on the geometry of the heater that's being used, we would directly get a value for C sub CR, but for a few of these, they depend on other quantities that need to be here, where K1 is defined according to this expression. So we only need to find K1 if it's a small horizontal flat heater. And the definition of it being small is going to be based on the calculation of L star. L star is defined by this expression, where it's a characteristic length that is L, where L would be the width or diameter. So if I have the width or the diameter of this small horizontal flat heater, if it's a circular heater, it would just be the diameter. If it's a, let's say, a square heater, we would use the length of one of the sides. But this quantity, L, will be substituted into this expression along with these fluid properties to get L star. If L star falls in between this range, then we would use K1 times, or 18.9 K1, in order to find C sub CR. And all that does is it gives us an expression of a magnitude for C sub CR that we use to get this expression that is the critical heat flux, or Q dot max here. Now, if we heat past that critical heat flux and get into the film boiling regime, this expression, we get another expression that we would use. Now here, notice it's significantly different with regard to its formulation. Now we still have the latent heat of vaporization, but now we have a specific heat of the vapor phase. We have a dynamic viscosity of the vapor phase. We still have the density difference between the liquid and vapor phase, but here it's that density difference is multiplied by the density of the vapor phase. Here we actually even have the thermal conductivity of the vapor phase. Now in this expression, now TS, TSAT, those are quantities we've seen before. Here, this is just the diameter of the surface, and we have this constant C film. But now going back to this thermal conductivity, the reason that we find the thermal conductivity of the vapor phase here is because conduction is the mode, the dominant mode of heat transfer once we get to this case of the film boiling. Now, just to go back to the schematic here, that has, let's see, here we go. Again, when we get to film boiling, there's actually a vapor film that separates the liquid from the solid surface. The solid surface is the place where nucleate pool boiling would occur, and that vapor would be converted from liquid into vapor on this solid surface because the liquid is actually in contact with the heated surface. Here for film boiling, none of this liquid water is touching that surface. So all the heat has to first go into the vapor film, and then we would have the nucleation of bubbles on the top surface of that vapor film where the water is actually in contact with it. So the correlation that is defined for the film boiling looks a lot different. And that's just because the mechanisms that are responsible for the heating are different. So we would just write an expression for the heat flux during the film boiling condition that would be according to this expression again, where all of these properties would still be evaluated at the saturation temperature for the fluid, because whether it's film boiling or nucleate boiling, that water, if it's water, typically it is water that is the working fluid, but that water is at atmospheric pressure. The saturation properties don't change, because at a saturation condition, the temperature, the saturation temperature is directly linked to what the atmospheric pressure is around that, or what the pressure is for that fluid. So if it is exposed to the atmosphere at 1 atmosphere or 101.325 kPa, then the saturation temperature is just set at 100 degrees, and we would evaluate all these properties at that particular temperature. But this heat flux associated with film boiling is not one that's actually used very often, because this is not a place that we actually want to operate. Because again, when we look at the expression of the pool boiling curve, now I can just use this one. If I have a particular heat flux that I want to get into the fluid, I could do it in the nucleate pool boiling range, or I can do it in the film boiling range. This is accomplished at a much lower temperature, T1, I'll just call it T1, or let's say T nucleate. And here, this would be associated with film boiling. So the excess temperature required to get the same heat flux during film boiling is much higher than compared to this heat flux in the nucleate pool boiling range. So, excuse me, that correlation is defined, but again, it's not a place that we want to operate, which equation we use for natural convection. Ricardo, I was saying that in the natural convection, the natural convection expression would be in chapter 9, because it's not actually boiling. There are no bubbles being produced. Transition boiling is an expression that is also not included in your text, because it's only obtainable using a temperature controlled experiment, which is not done at all in practice. So it's not presented in this text. So when we write these expressions for these heat fluxes, the expressions for the heat fluxes are just different, because the mechanisms responsible for the heat transfer are significantly different, and they require that you take into account different phenomena that are actually responsible for getting heat from the solid surface into the fluid that's actually being boiled here. And typically it's going to be water. And actually, before I move on to condensation, I want to just look at an example of how we would go about getting properties and selecting the appropriate correlation for that particular problem. So let's say we have a heating element. Let's see here. That is just for boiling water here. And to accomplish the boiling of the water, we're going to consider that we have a heating element that is actually submerged in the water, so that let's say I have some water here. And instead of heating it by a heat flux, let's say from the bottom, like you would have a pot of water, we're going to consider a heating element. So let's see, I'll just draw this one here in green. So we have this heating element. And from the heating element, we have a heat flux. Actually, we'll just consider it from the perimeter here. A heat flux from the surface that will be supplied in order to heat the water so that we get nucleate boil, or get some nucleation of bubbles to occur from this surface so that we're generating vapor bubbles, meaning that we'll be able to take advantage of the heat transfer associated with phase change. If we don't produce any bubbles, we actually don't have any phase change occurring, so that we wouldn't be able to take advantage of that change in phase from liquid to vapor. There's an additional amount of heat that can be removed from the surface when bubbles actually are formed, because we're adding that additional energy that is required to change the phase, which is the latent heat. So here we're going to consider that the water temperature is 120 degrees C, and is saturated, meaning that it's just at a saturation condition. So if the water temperature is 120 degrees and saturated, that just means that there's a pressure around the water that's greater than atmospheric pressure, where the saturation temperature would just be 100 degrees. So if we increase the pressure, we would also increase the saturation temperature that is associated with it. And we can actually, when we go to the tables, we can look at, well, what would that pressure be? And here we want to consider that the surface temperature, the heater surface temperature, is 125 degrees C. And just to give some geometry here, the heater length is 65 centimeters, and its diameter is 2 centimeters. And here we're only going to consider that it's heating from its perimeter, not from the very end. So we can just leave that area off. So if we're using this heating element to heat the water to boil it, here we want to consider, well, what is the highest rate at which steam, well, what is the rate at which steam would be produced? So we can just add another concept here. What is the rate at which steam is produced, which is just the vapor bubbles. So here we have to calculate a few things. We definitely will need to find out, well, what is the heat flux, because the rate at which steam is produced, this steam production is basically just a mass flow rate, where this mass flow rate is just the rate at which liquid water will be converted into vapor. So we call that a mass flow rate. Well, the heat that is being added to the liquid water to get bubbles to be produced is just going to be some heat transfer rate. And the amount of heat that is being transferred, let's say Q dot from the surface, would just be equal to the rate at which water is being boiled, which could be written as the mass flow rate, which is just the steam production rate, times the latent heat of vaporization. Because that heat that is leaving the surface and going into producing these bubbles would tell us what this mass flow rate is. So if I rearrange this expression, the mass flow rate, or I'll just say the steam production rate, would just be equal to the rate at which heat is being used to boil the water divided by the latent heat of vaporization of the water. Now, this latent heat of vaporization would just be the latent heat associated with the saturation condition that is for the water being at 120 degrees. And the rate at which heat is entering the fluid, which is that boiling heat transfer rate, is going to be based on, well, in what regime would this boiling be occurring? Would it be natural convection, nucleate pool boiling here, or film boiling? Now, when we consider, well, what is the pool boiling curve? That pool boiling curve is based on, well, first, if we start with the lowest regime, which is natural convection. Well, in natural convection, no bubbles would be produced at all. It's just a movement of the water due to density differences that exist in the body of water, such that if no bubbles are being produced, we still have movement because the water molecules right next to the heater surface would move through the fluid upward and away from the surface, and cooler ones would come in to replace them, and we would get movement of the fluid. That would be the natural convection. But if we're going to produce steam, that means that bubbles have to be formed. So that rules out any expression of a heat flux by natural convection or a natural convection expression. Nucleate pool boiling would be the first one that we would have access to or consider if we're producing bubbles. And then we could also have film boiling. Now, when we look at the pool boiling curve, and I'll go back to the one that actually has, here, this is the pool boiling curve at 1 atmosphere. Now, our problem is a problem at which we're considering that the saturation temperature of the water is 20 degrees, which means that the pressure will be higher than just 1 atmosphere. But what happens when the atmospheric condition changes to this curve? Well, what ends up happening is that we end up shifting the curve. If I increase the saturation pressure, that means that the saturation temperature would become higher, and the temperature at which the temperature at which we would have to bring the surface would just be a higher temperature because the saturation temperature will be higher. But here, saturation, or for the saturation condition associated with a pool boiling, the temperature difference between the surface and the saturation temperature of the fluid, which is that excess temperature, it starts at about 5 degrees here and goes up to about 30 degrees. And this would occur whether it was a pressure of 1 atmosphere or 2 atmospheres or 3 atmospheres. The temperature difference between the surface and whatever that saturation temperature is just going to move, it will shift slightly to the left or right. It'll slip slightly to the right if it's a higher pressure, or shift slightly to the left if it's a lower pressure than atmospheric conditions. But the temperature differences are going to remain about the same for whether it's no matter what the pressure actually is. Now, this curve will completely change if we change the fluid, but we'll still have a natural convection, nucleate, film boiling, and transition boiling if it's a temperature controlled experiment. So here we can use this expression and consider that for a temperature difference between the surface that was 125 degrees and the saturation temperature is 120 degrees. For this problem, there's a 5-degree temperature difference. That would definitely put us in the nucleate boiling range and not the film boiling range. So when we're looking at correlations that would describe heat transfer that would be occurring from this surface when bubbles are being formed, and we only have a 5-degree temperature difference and bubbles forming, that says we're definitely in the nucleate pool boiling regime, not the film boiling regime. So that says, okay, now we have to limit the expressions that limit the choices of expressions that we have. When we look at these correlations for heat fluxes, that rules out the heat flux calculation for film boiling and for the minimum heat flux. Also, if it's only a 5-degree temperature difference, we're definitely not at the critical heat flux. So we'd have to consider the use of the heat flux correlation for nucleate boiling. And this is actually named the Rosenau, Rosenau, ROHNAU SENOW correlation. But again, it's just an empirical expression of the correlation that describes pool boiling when it's in the nucleate regime. So here, when we're calculating this heat transfer rate, Q dot boil is just the heat flux for boiling times the surface area over which that heat flux would be occurring. So in this problem, our surface area, if we're just considering heat transfer from the perimeter of the heater, just becomes pi dl. And our heat flux for boiling is that heat flux associated with nucleate pool boiling. Since we only have a 5-degree temperature difference, our excess temperature is just the surface temperature minus the saturation temperature here, which is just 125 degrees, minus the saturation temperature, which is 120 degrees. So this is just a 5-degree temperature difference between the surface and the water that is actually being boiled here. So this expression for the nucleate pool boiling is going to be by the Rosenau equation or correlation. This is the dynamic viscosity of the liquid phase times the latent heat of vaporization at 120 degrees times here the gravity of 9.1 meters per second squared times the density difference between the liquid and the vapor divided by the surface temperature raised, all this raised to the 1/2 power times the specific heat of the liquid phase times the Ts minus Tsat, which is just the excess temperature, divided by this constant C sub SF for nucleate pool boiling times the latent heat times the Prandtl number of the liquid phase raised to the N, and this entire quantity cubed. So we need properties that we can evaluate from the tables for water at 120 degrees. Now, just to list them here, I'm going to need the dynamic viscosity of the liquid, the latent heat, the density of the liquid phase, the density of the vapor phase, the surface tension, the specific heat of the liquid phase, the Prandtl number of the liquid phase, C sub SF, and N. So these properties are going to come from the appendix, and like the surface tension and these constants are going to come from the tables here. So just going to the tables first from 10 dash, I can't remember the letters, or I'll go back to them, but C sub SF, and N are going to be dependent on the material that the surface is actually made of. So here I have to specify that this heater is made of a particular type of material to get C sub SF and N. So they will only slightly affect the total expression of the heat flux for boiling, and we'll look at why that is, and that's just through the definitions of these quantities that are experimentally determined. Let's say for this heater, see heater surface, and we'll say this heater is made of brass here, one of the materials that's in that table, and we'll look at, well, what is the effect of the property. Now, the reason that this has to be considered is recall that when nucleate pool boiling is occurring, liquid is being changed to vapor on this surface, and the rate at which bubbles can be produced and move away from the surface is going to affect the heat flux that can be calculated. Well, different surfaces or water interacts with different material surfaces differently, such that the surface tension that occurs between each of these, between water and the actual surface changes. And so the rate at which bubbles can be nucleated is going to change. And so we have to take into account through the Rosenau correlation, the expressions of these experimentally determined constants here. So if we use brass, and I go back to those tables, where again, these tables that have C sub S, F, and N are only going to be used for the Rosenau correlation, where we have the nuclear pool boiling occurring. So we have water and copper, stainless steel, water, brass here. So it says here that the value of C sub SF is 0.006 and N is 1. Now notice for all of these expressions that have water with a given surface, N is equal to 1. And the value of C sub SF here, looks like the lowest value is 0.0058. The highest one is 0.013. So here, these values of C sub SF, they vary quite a bit, but it's going to be dependent on the condition. Notice here that for copper that's polished and copper that's scored, meaning it just kind of is scratched, such that this provide more nucleation sites, because there are little scratches where water vapor can be produced much more easily than if it's polished. But when I look here at polished copper, 0.013, stainless steel that's polished, 0.013, and here's stainless steel that's ground and polished, get a slightly different value here. Water and brass, or water, brass, water, nickel. Now this is without any consideration for the surface preparation, but these values that are associated with this calculation of the nuclear pool boiling are just all experimentally determined values that we substitute into this expression. So they do slightly affect the value of the heat flux based on the formulation of that particular correlation. So 0.006 and 1.0. All right, so for those two quantities, 0.0060 and 1.0 for those two quantities from table A3. And these properties that we need, actually, we're going to get the surface tension. Surface tension we can get from the another table that I just presented there. Oops. Go to the figures. The surface tension for water at 120 degrees, 0.0550. Again, the properties are going to be evaluated at the saturation temperature for the water. So this is not an average temperature or anything. This is just the saturation temperature for the water. So 0.0050 newtons per meter. 0.0550 newtons per meter. Now, all the other properties are going to come from table A9, which are just the saturation properties for water. All right, so properties of saturated water, and here we just want them for 120 degrees. And just to, as I said before, we can look up, well, what is the pressure that will be associated with the 120 degrees? You know, for boiling of water at atmospheric pressure, 101 typically we take it as 325, but 101.33, which would just be a standard atmosphere. Water boils at 100 degrees, but if we want to boil it at 120 degrees, the pressure would have to be 198.53 kPa rather than 101.33 associated with boiling at 100 degrees. So the properties associated with that saturation condition change. And so the ones that we need here, we need the density of the liquid phase, the density of the vapor phase, the latent heat, of vaporization, the specific heat of the liquid phase. We also need the dynamic viscosity of the liquid phase and the Prandtl number of the liquid phase. So those are all properties that we need in order to substitute into the expression for of the Rosenau correlation to calculate that heat flux. So 943.4 for the density of the liquid phase, the density of the vapor phase, 1.121 kilograms per cubic meter. The dynamic viscosity, well, here, I think the latent heat was next. So the latent heat was 2,203 kilojoules per kilogram. Zoom out a little bit here. The specific heat, C sub PL, 4,244. And this is kilojoules per kilogram Kelvin. We also need the dynamic viscosity of the liquid phase, 0.232 times 10 to the minus 3. 0.232 times 10 to the minus 3. Kilograms per meter second. And the Prandtl number for the liquid. The Prandtl number is 1.44. So now we have the properties of the fluid that we need to substitute into this expression to get the heat flux that is due to nucleate pool boiling with this 5-degree temperature difference that is here. So we're going to substitute in these expressions, and actually we're going to write the properties. So there's a reference here. Kilograms per cubic meter. Kilograms per cubic meter. This is kilojoules per, no, this is 4,000. So this is joules per kilogram Kelvin. And the Prandtl number is unitless, and these other two are also unitless. So now we have all these properties that are assessed, and I'm going to just substitute them in for this first expression here. Then, so the nucleate pool boiling heat flux then is this dynamic viscosity. It's already in basic units, so this is 0.232 times 10 to the minus 3. Let me write that again. The latent heat of vaporization, now this is in kilojoules, so we want to make sure we get that to basic units. So this will be 2,203 times 10 to the 3 to make that joules per kilogram. Use a gravitational constant of 9.81 meters per second squared times this density difference. These are already in kilograms per cubic meter to basic units, so 943.4 minus 1.121. The surface tension is in newtons per meter, and Newton is just a oh my goodness, I'm forgetting that already. Kilograms times meters per second squared. So here we have just a basic unit, 0.055. And this is raised to the 1/2 times the specific heat of the liquid phase. The specific heat here of the liquid was 4,244 joules per kilogram Kelvin, so that's already in basic units. The surface temperature, or this surface temperature of 125 minus the saturation temperature. This first constant, 0.006. The latent heat of vaporization, again, this is in kilojoules per kilogram, so this has to be multiplied by 1,000 to make it basic units. 2,203 times 10 to the 3. The Prandtl number for the liquid phase, 1.44, raised to the n, which is just 1. And this entire quantity cubed. So this expression written in these basic, with all of the quantities in basic units, allows us to then be able to determine what this heat flux is by boiling, particularly in the nuclear pool boiling regime. And here this should be about 290,300 watts per meter squared for this heat flux. Now this will be the rate per unit area that heat is moving out of the surface of that heater into the water. So this expression will allow us to calculate now what is the heat transfer rate, which will be this 290,300 watts per meter squared times the surface area. The surface area, the diameter here was 2 centimeters, 0.02 meters times the length of 65 centimeters, 0.65 meters, so that we get meters squared times these watts per square meter. And we can calculate now, well, what is the heat transfer rate actually into the water? So here, this expression then is heat transfer rate of 11,856 watts. So that's the heat transfer into the water, so that now we can determine, well, what is the mass flow rate, or the rate at which vapor is being produced on this heater. So that this is that expression of the amount of heat that is going into changing the phase of the water, so that there is vapor being produced from the liquid. So here, this mass flow rate, or this rate at which vapor is being produced, again, is just the heat transfer rate by boiling divided by the latent heat. So here this would be 11,856 watts divided by the latent heat of vaporization, which is 2,203. That would be joules per kilogram, or 2,203 times 1,000 joules per kilogram. So I can get basic units that are just going to be kilograms per second. Okay, so here are the kilograms per second that will be produced. Here, it's 11,856 divided by 2,203. All right, so I get here 5.38 times 10 to the minus 5 kilograms per second, or let's do this per hour. There's 3,600 seconds in an hour. So let's multiply by 3,600. All right, so this will be 19.37 kilograms in an hour, as that expression per second is pretty small. So if we were running this heater, this is the rate at which vapor is actually going to be produced from this surface. Now, we can consider, if I changed the heater material, so if I had kept everything else the same, but I just selected a heater with the same dimensions and sought to have the same temperature difference between the heater and the water that is being boiled, well, changing the material type is just going to change the expression of C sub SF and N. So I'd get a slightly different value for the heat flux that is provided by the nuclear boiling, And thus I would end up with a slightly different expression for the rate at which heat is going to be a slightly different rate at which the heat is being used to actually convert the water to water vapor. Now, if I change the saturation temperature, let's say I wanted to boil the water at 100 degrees, so just at atmospheric pressure rather than at the elevated pressure that will be required to get the water to boil at 120 degrees. Well, that will change all of the properties that are associated with the calculation of this heat transfer rate by nuclear pool boiling. Thus, the heat transfer rate will be different, and the mass flow rate, or the rate at which vapor would be produced, is going to change slightly. So in that problem, or in this problem, not only do the fluid properties change as a function of that saturation temperature, but it would also change as a function of the material type that is actually used in order to determine the rate at which vapor would be actually produced on one of these surfaces. Now, this heat transfer rate, well, for most engineering applications, when we're considering boiling, just going back to this expression of the pool boiling curve, when boiling is being used for heat transfer, whether that be in a heat exchanger or whether that is for flow boiling, or if it's a boiler, this expression or this range is where we typically operate, which is the nuclear boiling, because again, for the same heat flux, if we're operating in we have a choice of operating in nuclear or the film boiling range. If we want to support a given heat flux, again, we're not considering this transition boiling because this is not a place that you can get to with a heat flux control problem. But here, when we consider these temperatures that are associated with the surface temperature, because again, this excess temperature is just the surface temperature minus the saturation temperature. So the saturation temperature would be considered a constant here. If I can get this particular heat flux at this temperature, well, it just says, as long as I have materials that don't melt at these temperatures above the saturation temperature. So if I'm boiling water at 1 atmosphere, this surface temperature only needs to get up to maybe about 120 degrees or so. But if I want to support the same heat flux and I'm considering film boiling, that same temperature will probably be around 800, 900 degrees. And so that material that is being used to do the boiling has to be one with a much higher temperature, and any other components or any other surfaces that are in contact with this water at these much higher temperatures, or these surfaces that are used to heat the water at much higher temperatures, those would also need to be able to maintain their structural integrity at these much higher temperatures. So this range here from A to B to C is the place where we typically want to have boiling occurring. Film boiling is usually only achieved during a malfunction, and that the importance of this Leidenfrost point is that, let's say there's some issue with the supply of water to the surface, or let's say a problem associated with the heating element, such that we get past this critical heat flux and we end up over here in film boiling. Well, the Leidenfrost point tells us, well, in that emergency situation, we're going to need to get the heat flux to drop to below the Leidenfrost point in order to break up this vapor film that would form during film boiling to get us back down into the nuclear pool boiling regime and then down into natural convection and eventually turning it off. But these expressions just allow us to write expressions of the heat flux with relationship to the excess temperature that is associated with this phase change process that we call boiling. Now, on the other side, or the opposite of boiling, is condensation. And the condensation is the conversion of the vapor back into a liquid. And most closed processes where we are using boiling as a mode for heat transfer, well, we also would have condensation to change that liquid water that we converted into vapor back into a liquid. So if we're considering something like a steam power plant, in the boiler, we would have boiling occurring, but in the condenser is where we would condense this slightly superheated steam or saturated steam back into a liquid. And in this text, we won't go into depth with the correlations for condensation, but I definitely want to consider the physical mechanisms associated with condensation. Here, when we consider again condensation, this is going to occur when the temperature of the vapor is reduced below its saturation temperature. So if the saturation temperature, let's say, is 100 degrees for 101.33 kPa, just from the table A9 that we just referenced. If the surface temperature is below 100 degrees C, then we would have condensation occurring because the saturation temperature is higher than that surface temperature, and thus droplets would start to form on that surface. Here in this figure that I pulled from your text, these are examples of the two types of condensation that we typically consider: film condensation and dropwise condensation. Now, when we consider physically what's happening in both, vapor would be out in front of each of these surfaces, and they will be forming liquid on this solid surface here, where the solid surface is indicated to have a temperature of 80 degrees. So 80 degrees is much less than the 100 degrees C that will be associated with steam at 1 atmosphere out in front of both of these plates. But what happens physically when the droplets form on the surface due to the condensation process, if it's film condensation, as the condensation occurs, that condensate will wet the surface and form this liquid film. So here, this is a vertical surface. And here, this is a liquid layer that is shown here to be increasing in thickness as we move downward here. So gravity is moving, or is in the downward direction, so that the fluid will flow downward as it condenses. Well, let's say the liquid flows downward as the vapor is condensing on the surface. Now, the significance of this liquid layer is that it will blanket the surface and provides a resistance to heat transfer. Because again, say what the vapor is at 100 degrees C. So during this condensation process, the heat is leaving the vapor and going into this surface at 80 degrees C. But the liquid layer that forms is a resistance to the heat transfer that will be occurring. So if this is a saturation condition where the temperature of the vapor is 100 degrees, well, heat transfer would occur to this upper surface of this blanket of liquid that is forming over the surface. And it would be at about the same temperature, 100 degrees, because the condensation process is a saturation process, so that the liquid water that is on the very top of this film is at 100 degrees. And as we move closer to the surface temperature would be 80 degrees. So we'd have a temperature variation in this liquid layer that forms, and it would be a resistance to the heat that will be moving from the vapor into this film and eventually into the surface at 80 degrees. This is the common mode, or this is the common physical phenomena that occurs during condensation when we're considering a condenser or any surface that is has liquid condensate forming on it from a vapor. And this is going to occur whenever we have what we call a hydrophilic surface. A hydrophilic surface is one on which water tends to spread and attach itself to. In a opposite manner, we have what we call dropwise condensation. This is what's called a hydrophobic surface, in that the water will bead as it condenses on this surface. Here, instead of the water forming as a film or a blanket, here the water forms as droplets, and those droplets will just slide down once their weight is greater than the surface tension force that holds the droplet to the surface. So that if it's a hydrophobic surface, something like a surface that would result when you apply something like Rain-X to the windshield of your car. If it's a fresh coat of Rain-X, if you've ever driven out on the highway and it started raining, you don't even have to use your windshield wiper blades, because the surface tension that exists between the water droplets and that surface is so low that just the airflow and the drag that occurs between the droplet and that air that's moving over your windshield just pulls the droplets right off of the windshield, and so you don't need the windshield wiper blades. So here, if I have a hydrophobic surface, the weight of the droplet that is required to overcome the surface tension of the forces is very little, and thus the droplets can be very small and still just slide right off the surface because the surface tension is so low. But if you've ever applied Rain-X to your windshield or some other hydrophobic surface or material that provides a hydrophobic surface, you know it has to be reapplied. And that's because there aren't any naturally occurring hydrophobic surfaces out or in any of the materials that we use for typical engineering applications. They all will form what is called a hydrophilic surface, in that it's easily wetted. So here you get much higher heat transfer rates because you don't have the resistance of this film to the heat transfer that would occur from the vapor into this cool surface, or this surface that's below the saturation temperature. Here, there's no resistance to heat transfer due to a liquid film because the droplets just roll right off the surface. And depending on the conditions, the rates of heat transfer that you can get with dropwise condensation can be as much as 10 times that for a condition where you have film condensation, because of the resistance to heat transfer that is going to be that will exist because of the film condensation. Now, when we're considering heat transfer rates by condensation, here we say due to the film that forms, the heat transfer coefficients become a function of the film characteristics. That has to do with how thick is that film and what is the flow like, because here the flow of the fluid is going to be a function of the rate at which condensation is occurring on it. And in your text, they talk about flow regimes, for this film, such that they're defined as wave-free and wavy, which is a wavy one is like what's these velocity distribution that's drawn here in the thickness in these darker blue lines here. That would be a wavy film, and it's typically considered to be laminar, and there's a turbulent condition for fluid that is essentially falling off of the surface. I won't cover those particular expressions that are used to calculate the heat transfer coefficients, H, but they're going to be a function of what is the characteristic of this film. Is that film moving with a laminar flow condition or a quote unquote turbulent condition that is defined in your text? That will define what type of expression you should use, because the heat transfer Q dot, or the heat flux by boiling, will be a heat transfer coefficient here times the saturation temperature minus the surface temperature. Now again, here this expression of T sat minus TS is an expression for a saturation condition for the vapor that is now condensing on not boiling. It's not Q dot boiling. This is Q dot condensation. So this is for heat transfer from the vapor into this surface. Now this is, when I write it as the saturation temperature minus the surface temperature, this is for a condition where it is a saturation condition for the vapor. So here we have saturated vapor. Now, what happens if we have, instead of saturated vapor, slightly superheated vapor? For superheated vapor, this heat flux by condensation is still defined the same way, except that the temperature difference now would just be the temperature of the vapor, T sub V minus TS. If it's saturated vapor, it just means that we only have to remove enough energy from the vapor to get it to become a liquid based on the latent heat of vaporization, because recall that the latent heat of vaporization, HFG, is just Hg minus Hf. But if it's superheated, that means whenever this condensation is occurring, superheated vapor just has more energy in it than the vapor. This vapor has more energy in it than the vapor that exists during the saturated condition. So if I want to get superheated vapor to eventually become a liquid, I have to remove the energy that is required to go from a superheated vapor down to a saturated vapor, and then from a saturated vapor down to a saturated liquid. So here is still a heat transfer coefficient, but the temperature of the vapor minus the surface temperature is the temperature difference that would be used when it's a superheated vapor rather than just a saturated vapor that we're trying to remove heat from. Now, when we're considering that amount of heat that has to be removed or added, this heat transfer coefficient is just going to describe, some quantity that's multiplied by that temperature difference to get that heat flux. But when we're considering this condensation, recall that if this temperature is below the saturation temperature for the fluid, then the latent heat that would be used to, let's say, calculate a rate at which water would be condensed, we have to kind of modify the latent heat if we're going from, well, actually, I'll consider these situations here. Let's say we go from, say we start with and finish, well, let's say start and end. Let's say I have saturated vapor, and I go to saturated liquid. How would I describe the latent heat of vaporization? Well, this is just Hg minus Hf would just be HFG, because I'm going from saturated vapor to saturated liquid. So what would that look like? That would mean that I have a surface temperature that is the same as the saturated vapor, and I'm getting liquid water. If I get liquid water to condense on that surface, the only energy that was removed from the vapor was exactly the latent heat, in that I went from an enthalpy of the vapor phase to the enthalpy of the liquid phase. But let's say I go from superheated vapor to saturated liquid. Here, I would have to consider, let's say I will say H superheat minus H of the liquid to give me what we call an HFG star. So what is here we consider the enthalpy of the superheated vapor minus the enthalpy of the saturated liquid. This is still an enthalpy difference, but we would call it an HFG star, in that this is just a modified expression of the latent heat of vaporization when we're going from superheated vapor to saturated liquid rather than saturated vapor to saturated liquid. Let's say I went from superheated vapor down to a subcooled liquid. Recall that a subcooled liquid is just a liquid that is below the saturation temperature. So if you have a glass of water sitting next to you now, that is classified as a subcooled liquid. If it's about room temperature, it's probably 22 or 23 degrees C. If it's atmospheric pressure in the room that you're in, the boiling temperature or the saturation temperature associated with atmospheric pressure will be 100 degrees C. So if your water is, let's say, at 20 degrees C, that means there's 80 degrees C temperature difference between the state at which your water exists in the cup at 20 degrees and 100 degrees, which would be the saturation temperature. So if I wanted to get that water up to the point of boiling it, I'd have to first get it from 20 degrees all the way up to 100 degrees before it would start to boil. So here, when I'm considering going from a superheated vapor down to a subcooled liquid, here I'd have to consider H, the enthalpy of the superheated vapor, minus the enthalpy of the subcooled liquid now. And that we could define an HFG star, which would be another expression of a modified latent heat of vaporization for a condition where I'm going from superheated to subcooled. We could also consider, let's say, saturated vapor to subcooled liquid. In that case, this would just H sub G, the enthalpy of saturated vapor, minus H subcooled. We could call that an HFG star, where each of these expressions of an HFG star would have a different equation associated with it according to what the phase is of the vapor and what the end state is for the liquid. For the liquid, it's either going to be a saturated liquid or to be a subcooled liquid. For the vapor, it's either going to be a superheated vapor or a saturated vapor. So we have these four combinations that we can consider. So if I'm just operating between the saturated conditions, then it's just HFG. If I'm operating between the superheated vapor and saturated liquid, I get an expression for HFG star, a superheated vapor and a subcooled liquid, or saturated vapor and a subcooled liquid. Now, just to show you schematically, what does this look like from thermodynamics? Here, if I consider the vapor dome, and let's say here a line of constant pressure, so here this would be temperature pressure and enthalpy here. This dot right here, this is saturated vapor. Here, this is saturated liquid. Out here, superheated vapor. And over here, subcooled liquid. So on this plot here, this would be H sub F, and this would be H sub G. So if I'm removing, so in the first case, saturated vapor to saturated liquid, that just means I'm moving from saturated vapor over here to saturated liquid, and that's the enthalpy difference between the fluid. If I move from superheated vapor to saturated liquid, that means I'm starting here at the same pressure for a superheated vapor. Well, I have a larger value here, and if I'm using what I wrote here, H super, here would be H super here. So I'm moving from the enthalpy of the superheated vapor down to the enthalpy of the liquid, down to the enthalpy of the saturated vapor, then down to the enthalpy of the saturated liquid. So that's why I wrote here H super minus HF. If I want to go from superheated vapor to a subcooled liquid, I have to go from superheated to saturated vapor to saturated liquid, then down to saturated, or subcooled liquid here. So here, this is, I call H subcooled down here. And then finally from saturated vapor here to a subcooled liquid, I start with HG, have to go all the way down to HF, and then down to H subcooled here. So this is HG minus H subcooled. Each of these has a different expression associated with it. And the reason we define this is let's say we were considering the rate at which we are producing condensation. So if I have a heat transfer rate defined for condensation, which is going to be that rate at which heat moves from the saturated or from the vapor, where it could be saturated vapor or superheated vapor, into a surface where condensation is occurring. Well, this will just be written as a heat transfer coefficient times the surface area where condensation is occurring times the temperature. So I'm going to write this as the temperature of the vapor minus the temperature of the surface. This would be also equal to the mass flow rate times HFG. And I'm going to say HFG star here, because if it's a superheated vapor going down to the surface temperature, depending on what that surface temperature is, that will be the lowest temperature for the liquid water that will be forming during a condensation process. Now, when, of course, HFG, just to write this again, HFG is just HG minus HF. This is the quantity that you find in the saturation tables for a given problem. If I have a case where I'm going from, if we wanted to modify this, let's say where I'm going from a saturation condition for the vapor down to a subcooled liquid. So here, HFG star, here will be HFG plus 0.68 C sub PL times the saturation temperature minus the surface temperature. This is what we would use as an expression where we're going from saturated vapor to subcooled liquid here. That's how we would define that expression. If we were going to go from, let's say, a superheated vapor to a subcooled liquid, this expression would be HFG plus 0.68 C sub PL TS or TSAT minus TS plus C sub P of the vapor times the temperature of the vapor minus T sat here. This is if I'm going from a superheated vapor to a subcooled liquid. Now notice when these two expressions, there's just an additional term when I'm going from superheated vapor to subcooled liquid. This term C sub P of the vapor times the temperature of the vapor minus the saturation temperature. Remember, this is the saturation temperature here. It's the temperature at which the liquid and the vapor both exist. So I actually write that this is saturated vapor to saturated liquid for that very first expression. That is, it's not a star, it's just HFG. So if I'm just going from saturated vapor to saturated liquid, the rate of condensation is just the mass. This would be the rate at which condensate is formed times what would just be HFG if it's saturated vapor to saturated liquid. So from here on the dome to here on the dome. But if I'm going from a saturated vapor all the way down to a saturated liquid, HFG describes the enthalpy difference between the saturated vapor and the saturated liquid. Now, since this is already a liquid phase, we'd be going down from the saturation temperature to whatever the subcooled temperature is, and that would be the temperature of that surface. So empirically, it was determined that we could express this additional change in enthalpy as I move from saturated liquid to a subcooled liquid as 0.68 times the specific heat of the liquid phase times the saturation temperature minus the surface temperature. This is when that surface temperature is below the saturation temperature, so that we can get we'd end up with a subcooled liquid that is formed on that surface. So that's because we removed enough heat to get it to become a saturated liquid, then more was removed to get it to become a subcooled liquid, where that would be just this surface temperature here. HFG star is defined here when we move from a superheated all the way down to a subcooled liquid. So if I look at these terms, HFG again describes the enthalpy difference between the vapor and the liquid phases. This first term will describe that heat transfer or that enthalpy change that occurs as we go from saturated liquid to subcooled liquid. This last term is a description of the enthalpy change that occurs as we go from superheated vapor to saturated vapor here. So this is the specific heat of the vapor phase, because it's all vapor out here to the right of the saturation dome. And this temperature difference is the temperature of the vapor minus the saturation temperature. So this last term describes that enthalpy change from superheated to saturated. The second term is from saturated liquid to subcooled liquid. And the first term is just saturated vapor to saturated liquid. Now we could also have, again, I think that last, we could have an HFG star if we consider, let's say, from superheated vapor just down to saturated liquid. That would be HFG plus C sub P V of the vapor phase times the temperature of the vapor minus the saturation temperature. What this describes is superheated vapor down to a saturated liquid. And that the second term describes enthalpy change from superheated vapor to saturated vapor. And the first term describes saturated vapor down to saturated liquid. So here we went superheated vapor to saturated liquid. So these expressions can be used in this expression for HFG when we want to take and consider, if I have this heat transfer rate due to condensation, well, what would be the rate at which condensate is actually being formed? It would just be this heat transfer rate divided by HFG star, where HFG star is just HFG if we're going from saturated vapor to saturated liquid. But for any of these other conditions where we're moving between an end state and a beginning state that is not just saturation conditions, we would use these other expressions in order to write expressions for HFG star. For the first two agents, should they have the same coefficient on C sub PL? Yes, they were both 0.68. Oops, yeah, I just wrote 8 twice here. It's just, yeah, they're both just 0.68 times C sub PL. So whenever we're considering the condensation, if we want to calculate a rate at which condensate is occurring, which is going to be some kilograms per second, we'd have to consider how we define HFG star. Now, again, the calculations of H are going to depend on the flow conditions. You know, if in here, there's only, let me just actually going to, rather than write the equations, we're going to consider for the film condensation. For film condensation, we consider there are correlations for the average heat transfer coefficient that are going to be based on expressions. Let's see, is it, I don't want to say, just to kind of group them. Well, for film condensation, we consider vertical, horizontal, and inclined surfaces. So you can imagine if I have a surface that is vertical compared to one that is horizontal compared to another that is inclined, when droplets or when liquid water forms on these surfaces, they'll move differently. If gravity is downward for each one of these conditions, the heat transfer rates associated with let's say exactly the same surface temperatures for each, exactly the same vapor condition, the heat transfer coefficients will be different. The heat transfer coefficients typically, for exactly the same conditions, the highest heat transfer coefficient you're going to get is for a vertical surface. The next lower one will be on an inclined surface, and the lowest one will be for a surface that is horizontal due to, if condensation is occurring, the rate at which that condensation can move off of the surface in order for more vapor to be exposed to a cool surface to get condensation to occur is going to affect what those heat transfer coefficients will be. And thus, the expressions for heat transfer coefficients are going to be a function of the geometry of the problem, in that how is the surface oriented so that fluid can move off of that surface. But now we also will consider that we can have laminar that is wave free. We can have laminar flow that is wavy. And wave free and wavy have to do with what the streamlines would look like as the fluid is moving over this surface when we have film condensation. And then we also have a turbulent condition, these are all based on Reynolds number ranges. I won't go through them because I don't plan to give you any problems where you have to actually solve these, but if it's a vertical, horizontal, or inclined surface, it's going to tell you, okay, this is the geometry or the orientation for the surface. Limit myself to, if I have a vertical one, I certainly would not consider correlations for horizontal or inclined surfaces. Then once I calculate the Reynolds number that will be associated with the condensation that would occur on this surface, according to that Reynolds number, I can determine whether it's laminar free, whether it's laminar wavy, or if it's turbulent, according to conditions that are that would exist for the fluid movement in whatever the flow direction is. And just for these ranges here, for wave free, this is Reynolds numbers that will be less than 30. Here, this is from 30 to 100 or 1800. And for Reynolds numbers that are greater than 1800, this is all in your text for whenever, if you ever wanted to calculate heat transfer coefficients, but you'd have to select or choose the appropriate correlation according to the orientation and also according to the Reynolds number, and calculate then the expression of the heat transfer coefficient so that we can write that Q dot by condensation is equal to that heat transfer coefficient that's according to the, the orientation and the flow characteristics times the surface area over which it's occurring times the temperature of the vapor minus the surface temperature here. Where the temperature of the vapor would be the saturated temperature if it's saturated vapor. The temperature of the vapor, if it was a superheated vapor, minus the surface temperature. But this is how we would define that heat transfer rate by condensation when we have a problem where we have film condensation actually occurring. Now, these expressions are going to be different because the physical properties associated with the fluids when they are moving over the surfaces are different. Now, for dropwise condensation, because the surface remains clear of any film that would be occurring, there's actually only one expression that well, I guess you could actually call it two expressions that are that would exist for dropwise condensation, such that the droplets just move off the surface. So if they move off the surface and keep that surface exposed directly to the vapor, there's only two expressions that are in your text. There are probably hundreds of different expressions for heat transfer by condensation when we have surfaces that we are going to consider, but the total breadth of all of those correlations is not appropriate for an introductory heat transfer textbook. Multiple references for boiling heat transfer design that are going to include all kinds of heat transfer coefficient calculations. Here, I'm just considering here flat surfaces. In your text, they do have some circular ones, tube banks. So let's say you have a bunch of tubes that are oriented vertically, and water is condensing off of each one of them in what we call a tube bank. The average heat transfer coefficient would take into account that that the heat transfer from each of these individual tubes is going to be different because we might have liquid water dripping from one down onto the other. Or if we staggered them, we'd get different rates of heat transfer for a given tube bank. But that's kind of beyond the scope of this course. But as we've seen in chapter 7, 8, and now 10, the way that the fluid interacts with the surface is going to affect what the overall heat transfer rate and the heat fluxes will be from those surfaces. And what we're doing is looking at ways to calculate that heat transfer coefficient given conditions that exist for that particular flow configuration. So here, just to write for the dropwise condensation. And here, these expressions are specifically for dropwise condensation on copper, because again, this is just a limited presentation in this text. For the heat transfer coefficient for dropwise condensation, it is 51,104 plus 2,044 times the saturation temperature, when that saturation temperature is between 22 degrees and 100 degrees. When the saturation temperature is greater than 100 degrees, it's just a single value of 255,510 for the heat transfer coefficient. So the units associated with both these expressions are just watts per meter squared Kelvin. So all this is saying is that when we look here for saturation temperatures of 22 to 100 degrees, well, the saturation temperature for water at 100 degrees or at 1 atmosphere is 100 degrees. So as I decrease the pressure, the saturation temperature will go down. And so if I'm considering drop-wise condensation occurring, the only quantity that we need is the saturation temperature in order to calculate what the heat transfer coefficient is. That will be substituted into this expression to find the heat transfer rate by condensation. If the saturation temperature is above 100 degrees, meaning that the pressure is above 1 atmosphere, we would consider that the drop-wise condensation that's occurring on a copper surface would be described with a heat transfer coefficient that is 255,510. Now, that's a really large number, and what that says is I don't need very much temperature difference between the vapor and the surface temperature to get a very high heat transfer rate. And that's because, again, this expression for the condensation means that there's a phase change that is actually occurring, in that we're removing heat from the vapor primarily by that phase change that's occurring in the vapor so that it becomes a liquid. So whether we're boiling water or condensing water, we get extremely high heat transfer rates for relatively low temperature differences because of the change in phase of the fluid, in that we're moving from an enthalpy associated with a vapor to an enthalpy associated with a liquid when we go through condensation. And during boiling, we're going from the enthalpy of the liquid to an enthalpy of the vapor. So when I look here back at the appendix, here I'm paying particular attention to the specific enthalpy, or here the latent heat of vaporization, and that the of the liquid and vapor phases are not individually given here. They're just giving you HFG. If you go into a thermodynamics text, you'll see HF and HG. But this is the amount of energy. HFG is that amount of energy that is added to the liquid to make it a vapor, or removed from a vapor to make it a liquid per unit mass, kilojoules per kilogram, without any temperature change having to occur. And so that's the importance of that saturation condition when we're considering boiling and condensation, is that when we get to that particular temperature, we can have heat transfer to occur without any temperature change in the fluid, and it enhances the amount of heat that is transferred by convection, whether it is heat transfer from the surface when we're going during a boiling process, or heat transfer to the surface when we're going through a condensation process. So this boiling and condensation, which we're looked at on a very macroscopic level when we consider particularly in thermodynamics 2, when you're going through cycles where we have heat transfer and heat transfer into a working fluid, whether that be a boiler for water, or an evaporator that is, let's say for R134A, where we have heat transfer into the working fluid and we're changing the phase from a liquid into a vapor. We're taking advantage of the latent heat of vaporization of that working fluid. In the condenser section of both for water and the condenser section for R134A, or just any refrigerant, we have a changing of phase from a vapor into a liquid, where we're again able to provide relatively high heat transfer rates into and out of the fluids based on a consideration of phase change that's actually occurring in the fluid at a constant temperature, that is the saturation temperature associated with the pressure for that boiler, that condenser, or that evaporator. So a lot of those processes that we see and didn't really consider the mechanisms associated with that heat transfer when we have phase change are represented in these expressions that we have for boiling and for condensation. Now, when we're considering boiling and condensation, many times it's not completely on its own. It's going to occur so that we can remove heat from a surface, let's say during boiling, or add heat to a surface during condensation. But if on the other side of that surface where we're either heating or cooling one fluid, we could be heating or cooling another fluid that is flowing past that same surface just on the other side. And that's where we would consider or call it a heat exchanger. Now, heat exchangers are places where heat is just exchanged between two moving fluids. And so that's what's covered in chapter 11. And this is where we'll bring together a lot of concepts from the previous chapters, in particular, chapter 8, where we had internal flow, and to some degree, boiling and condensation for particular types of heat exchangers. But when we're talking about heat exchangers, these heat exchangers involve two moving fluids. A hot fluid and a cold fluid. And those are relative. The one that comes into the heat exchanger with a higher temperature is the one that we will call the hot fluid. The one that enters with the lower temperature is the cold fluid. So in this heat exchanger, these are places where heat is exchanged between the two fluids without the fluids actually mixing. All they're doing is sharing their energy so that heat is transferred out of the hot fluid and into the cold fluid. Heat transfer naturally occurs from a high temperature to a low temperature. Now, in chapter 11, we'll talk about different types of heat exchangers, how we classify them. We'll consider how we do an energy analysis, or basically just an energy balance on the heat exchangers, and the two methods that are primarily used to actually analyze heat exchangers. Now, again, heat exchangers are probably one that you see or consider all the time if you do any driving, is your automobile radiator. That is we'll talk about what type of heat exchanger is that when we start to classify them. But your automobile radiator, in it is engine coolant that flows inside the tubing, and outside the tubing, we have air that flows over that radiator. So the heat transfer, we have heat transfer from the engine coolant to the air. So the coolant usually comes in either right to left or left to right as it flows through the radiator, and air flows front to back as either, if you're traveling, air is just moving due to the relative motion of the vehicle, or if there is a radiator fan that is on, it is actually pulling air, or actually, pulling air through the radiator so that heat exchange is occurring between the two fluids. In an automobile radiator, the engine coolant will be the hot fluid, and the air would be the cold fluid. This also occurs in the evaporator. An air conditioning unit, whether that's in your car or at your home. Here we have two fluids. We have the refrigerant, and we have air. Well, in the evaporator section is the section where the refrigerant is going to gain heat from the air so that it's cooling the air. In this case, the air is the hot fluid and the refrigerant is the cold fluid, so that the heat transfers out of the air and into the refrigerant, and the evaporator is that portion that is the heat exchanger that will be in your ductwork, whether that's the ductwork in the dashboard of your vehicle or the ductwork that is typically in the ceiling of your home. Here, the air is the hot fluid and the refrigerant is the cold fluid. In the condenser of your air conditioning unit, again, you have refrigerant and you have air, but in the condenser, the refrigerant is the hot fluid and the air is the cold fluid. So just like the automobile radiator, the refrigerant is going to give up its heat to the air that is actually flowing through it. And we'll look at, we'll kind of classify the types of heat exchangers, but no matter what the classification is for the heat exchanger, in a heat exchanger, we are giving up heat from the hot fluid and absorbing heat, that same heat, into the cold fluid. So here I've got a couple of figures, so I don't need to redraw all of them. Here on a TX diagram, generically, I just call it X, and that is some position. Here we have a hot fluid. This is what's called a parallel flow heat exchanger. Both fluids are moving in the same direction. But here the hot fluid is decreasing in temperature as it moves through the heat exchanger. The cold fluid is increasing in temperature as it moves through the heat exchanger. In another configuration, we have what's called a counter flow heat exchanger. And all that means is that the two fluids come in at opposite ends of a concentric tube heat exchanger. Still, the hot fluid decreases in temperature. The cold fluid increases in temperature. No matter what the flow arrangement is or the configuration is for that classification for that type of heat exchanger, those are the two things that always happen. The hot fluid loses heat, so its temperature decreases. The cold fluid gains heat because its temperature increases. Now, again, hot and cold only have to do with what are the temperatures of the fluid as they enter the heat exchanger. Here the arrow is from left to right here for the hot fluid. So it came in at a high temperature and the cold fluid came in at a low temperature or a lower temperature. The hot fluid comes in at this temperature. The cold fluid comes in at this temperature. So here, these expressions for hot and cold only have to do with the inlet conditions of the two fluids. When we compare the two inlet temperatures, the one with the higher temperature is the hot fluid, because in that heat exchanger, that its temperature will decrease. For the cold fluid, in that heat exchanger, its temperature will increase. Now here, this arrangement here, that we have the hot fluid flowing through the center and the cold fluid flowing on the outside. This is what we would call a double pipe. It's just a pipe in a pipe heat exchanger, or sometimes it's referred to as a concentric tube heat exchanger. Capital HX is just my shorthand for heat exchanger. In those two configurations, for the parallel flow heat exchanger, here we have the hot fluid coming in and the cold fluid coming in at what would be the same relative position in the heat exchanger, and they just flow in the same direction and give up their heat, so that the hot fluid is losing heat and its temperature is decreasing. The cold fluid is gaining heat and increasing in temperature. In this counterflow heat exchanger, the hot fluid is coming in from the left, the cold fluid is coming in from the right. They're exchanging heat as they flow past one another. Again, the hot fluid is still decreasing in temperature and the cold fluid is increasing in temperature. They're just flowing in different directions. Now, as it turns out, a counterflow heat exchanger for the same two fluids with the same flow conditions is always going to give you a higher heat transfer rate than a parallel flow heat exchanger. So if I took this heat exchanger and I just, in this case, I had the inlets connected at the same ends. And then after I finished that experiment, I connected the inlet for the cold at the other end. I'll get a higher heat transfer for the counterflow heat exchanger. And that's just because a higher temperature difference can be maintained between the two fluids when we have a counterflow heat exchanger. Whereas notice here for the temperature profiles, this temperature difference, this is the delta T that exists between the hot fluid and the cold fluid as they move through the heat exchanger. Here, this is the delta T that exists between the hot and the cold fluid. This delta T for the counterflow heat exchanger, you end up with a much higher average temperature difference along the entire length of the heat exchanger compared to the average delta T that exists when we have that everything kept the same except that we change the flow condition here, or the flow direction. So this double pipe counterflow heat exchanger is actually going to become the basis for the analysis of other configurations that aren't double pipe or concentric tube heat exchangers, but we will use this counterflow consideration as we look at how we develop expressions for heat transfer rates or performance of these different types of heat exchangers. Now, generally, we can group these heat exchangers into a few different types. Here, this is what is called these two expressions here are both considered to be what we call cross-flow heat exchangers. Now, cross-flow heat exchangers is the type of heat exchanger that the automobile radiator falls into. Also, the condenser and evaporators of air conditioning systems fall into, in that you have a tube that usually is going to carry the liquid. The tube is going to carry the liquid, and on the outside, you have a gas or a vapor. But in this configuration, you can have fins. So in a radiator in your car, the engine coolant moves through the tubes, there are fins, and the air moves on the outside. Now, the reason that fins are used is because if there are no fins, like in this configuration here, the heat transfer only occurs from the outside. If the hot fluid is moving through the tube, heat transfer only occurs from the outside surfaces of these cylinders into the air that will be moving around it. If I have fins, heat transfer can occur from the exposed surface of the tubes into the air, but then some of that heat will be dissipated into the fins, and I can also have heat transfer occurring from the fins themselves into the air once that heat is conducted the outside surface of the tube into the fin and the heat is spread. So, and this is the kind of configuration that is used for radiators and also used for evaporators and condensers in air conditioning systems. Those fins just enhance the efficiency of the heat transfer between the fluid and the solid surfaces. Now, when we have fins that control the fluid flow of the gas over the tubes as it moves through the heat exchanger, this is what will be considered both fluids unmixed. Of course, the fluid that is moving through the tubes is confined such that if I have these 7 tubes on the other end, on the backside of this heat exchanger, fluid comes into this pipe and goes out of the pipe. It doesn't move into other pathways for the fluid, as the fluid that came into each tube is exactly the fluid that goes out of that tube. When we have these fins, so that the air that is moving over the fins or between the fins and over the tubes, well, if I look at this first 2 set of fins, or here, well, this one and this one,
As I move from left to right, the air that comes in between these two fins is the air that goes out on the other side. And if I pick any two fins here, the air that comes in between two fins is going to leave on the other side. So this is what we would call both fluids being unmixed. In this configuration where there are no fins, we consider one fluid to be mixed. The mixed one is the one that here, as it comes into the left side of imaginary control volume, it can leave on the right side of this control volume. You know, the fluid that came in the top can move as it moves around these tubes. It could come out in the middle or at the bottom. The fluid that came in on at the bottom on this left side could come in and move around and come out over on the top side on the right side. This is the fluid that we would consider to be mixed, and the one that's unmixed is what flows through the individual tubes. So when we consider a cross-flow heat exchanger, it will be further categorized or subcategorized as cross-flow, both fluids unmixed, or cross-flow, one fluid mixed, one fluid unmixed. There's no such thing as a cross-flow heat exchanger where both fluids are mixed, because the fluid flow path of one of them is going to be confined to a tube here. Here we have one fluid confined to a tube, one fluid confined to a pathway through individual sets of fins. Again, we have one fluid confined to the tube, and the other one is allowed to flow freely over the bank of tubes here. So that's how we define those cross-flow heat exchangers. And this is the type of heat exchanger that is most common for air conditioning systems on the evaporator and the condenser side, and also in vehicle radiators. They're usually the both fluids unmixed type of heat exchanger. So cross-flow heat exchangers is a type of heat exchanger. We also have what are called shell and tube heat exchangers. Now, these are the types of heat exchangers that are used in a lot of industrial applications, like this shell and tube heat exchangers. And these have a large number of tubes packed inside of a shell. So the black line here is the shell. And the heat transfer takes place as one of the fluids, or as one fluid that moves through the tubes, is either giving up or absorbing heat from the fluid that is moving through the shell that is flowing around each of these tubes. Now here, this shell and tube heat exchanger is drawn with baffles, these black vertical lines here. And that's just used to direct the fluid as it moves through the heat exchanger. So here, the fluid that is moving through the shell, here, the shell inlet, it's forced to move around these baffles. And what that does is it just increases the amount of contact that occurs between the two fluids as they're separated by the tubes that the fluid that's flowing through the tubes would be moving through. If we didn't have these baffles, in the absence of these vertical lines, if this is the shell inlet and the shell outlet, this fluid would just seek to move this way, like this. And you'd have very little contact between the two fluids on the inside and outside of these solid surfaces that separate them. But by using the baffles, you can direct the fluid flow. So you get more heat transfer, but it also increases the pressure drop for the fluid that's moving through the shell. And then on the other end, you have fluid that moves in through the tubes. So here, this is what would often be used for chilling air. The chillers that are used to cool the air that is in a lot of the buildings on campus has air moving through, and typically the air is going to move through the shell, and the chilled water that comes from one of our chilled water plants will move through the tubes. And there's heat exchange that occurs between the two. So the air will be the hot fluid, and the water, the chilled water, will be the cold fluid. The chilled water would increase slightly in temperature, and the air temperature would decrease significantly because the specific heat of water is so much higher than air. We can get a huge air temperature difference in the lowering of that air temperature, while the water only experiences a very small temperature increase because its specific heat is so high. But we'll stop here. I'm a minute over, and we'll pick up and with heat exchangers and get into some of the analysis of these different types of heat exchangers on Wednesday. All right, that's it. And I should have your exam grades posted, etc., later on this afternoon. All right, that's it. And I will see you on Wednesday or Tuesday during my office hours. All right, have a good day.